Welcome back to our discussion on ionic compounds. In section 1, we learned how to form ions, and we looked specifically at the properties of cations and anions. Section 2 is when we looked at the formation of ionic compounds and discussed the properties of them. Today we're going to start section 3. Today we're going to look more in depth at section 3, where we're going to learn how to name ionic compounds and write their formulas. We will start with writing ionic compound formulas. When we write ionic formulas, they have to be written in such a way that the positive and negative charges are balanced so that they're equal. For instance, if we had 2 plus, we want to make sure we have a 2 minus. That way the charges can create a neutral compound. The easiest way to do this is to crisscross the numeric values, or what I call the exchange of numbers, or the swoosh and reduce method. So we're going to exchange the numbers and then simplify so that it is in its smallest or simplest form. When performing the swoosh and reduce method, the first step we're going to do is write down the chemical symbol for each of the elements involved. We're going to make sure that we write down the metal first. Then we're going to add the charge of each of the elements as a superscript, so up top above the respective chemical symbol. Our third step is where we're going to exchange numbers. So we're going to crisscross the charges. So we're going to make the superscript the subscript of the opposite element. And then we're going to write the formula out, dropping the pluses and the minus signs, and we're not going to write any ones. We're going to check to see if it can reduce any, and if it can reduce, we must do that, and then rewrite the formula if we reduced. And then we're just going to check that the formula is neutral. A couple of things to watch out for is our polyatomic ions. These are going to be placed in parentheses, and we can never change any of the subscripts of the atoms within those brackets. They have to be treated as a unit when we write the formulas. So we're going to write it down as we see it, and our polyatomic ions are found on the back of our periodic table. They have listed the formulas, the charges, and the names on the back of the periodic table. The other thing we need to watch out for are Roman numerals. These occur mostly with transition metals because, if you'll recall, the transition metals have a variable charge, meaning they can have a 2 plus charge, a 3 plus charge, a 4 plus charge. It just depends on the element and what it's bonding to. So, in addition to the transition metals, lead, tin, and antimony are also treated with Roman numerals because they have variable charges. So what we're going to do is we're going to identify the number in parentheses for the Roman numeral, and we're going to use that as the charge. So whatever the Roman numeral is the charge on the metal. So the first name. We have a few practice problems that we can go through. Notice that I have it so that we are going to see each step for our first example, but then we're going to merge steps 1 through 3 in one step essentially, and then finish them out with 4, 5, and 6. Alright, so recall our first step is just to list out the elements involved. So we have lithium and phosphorus. Alright, for this first example, I'm going to go ahead and write out what I stopped with the previous step, so that I can start this step with it. And we can see what's happening at each step. Alright, so in the second step we're supposed to add the charges. So lithium is found in 1A, and it loses 1 electron, so it becomes 1 plus. Phosphorus is in 5A, so it's going to gain 3 electrons and become 3 minus. So again, I'm going to go ahead and, before we start step 3, write out where we left off with step 2. Alright, in step 3, we're going to crisscross or exchange numbers. So what I'm going to do is I'm going to circle the charge, and I'm going to show with an arrow where I'm transferring it. Circle the charge and crisscross. Great. Now, step 4 is where I'm going to write out the formula. So I'm going to look at the opposite atom, essentially, to see what number to give them. And we're going to write these numbers as subscripts, so down low. So I have Li, and Li received a 3 from phosphorus. And then I'm going to write the P, and P received a 1 from lithium, but we don't write 1s. Now I need to check to see if it simplifies, and it will not simplify. So anytime the formula has a 1, it will not simplify. Anytime that formula has both of them are even numbers, they will always simplify. Okay, so no simplification for this one. And then the last step is to check charges. So what I'm going to do is I'm going to identify the number of each of the elements and then multiply it by the charge of the elements. And then check those charges to make sure that they are equal. So lithium had 3 atoms, and we're going to multiply it by lithium's charge of a 1 plus. So lithium provides 3 plus to our compound. There is only 1 phosphorus atom, and phosphorus's charge is 3 minus. So when I multiply that across, I get 3 minus. So they are the same number, opposite sign. They will balance out and be 0 or neutral. Okay, our next example will go a little bit faster because I don't have to write out each of the steps. So when we look at magnesium and chlorine, we have to write out elements involved, then add the charges, crisscross, write the formula. Remember, we're going to look to see what the other element gave to us. So magnesium received a 1, but we do not write 1s. Chlorine received a 2. We're going to check to see if it reduces. It will not reduce. And then we're going to verify that it is balanced. There's 1 magnesium at a 2 plus charge. There is 2 chlorines at a 1 minus charge. We're all good. Our third example, aluminum and nitrogen. Step 1, write out the elements. Step 2, add charges. Step 3, crisscross or exchange numbers. Step 4, rewrite the formula with the new numbers. Again, we got those from the other element involved. Step 5, we need to reduce, and since they're both 3s, we will reduce it to 1s, and we don't write 1s. And then check charges. There's 1 of each, so I've got a 3 plus and a 3 minus, and it's going to balance out to 0. Good. Now our next example is going to include one of those polyatomics that we talked about that's located on the back of our periodic table. So you'll want to make sure you have your periodic table, by the way. Didn't mention this at all. Alright, so we're going to follow the same steps where we're going to write out each of the pieces of our compound. Then we're going to add charges, and when you look at the back of your periodic table, you will see that CO3 has a 2 minus charge. We're going to crisscross those charges and then rewrite. So Ca received a 2, CO3 received a 2. These can be reduced. And so when they reduce, they'll reduce to a 1, and we don't write 1s. And then we got a 2 plus and a 2 minus, and we are balanced. And then our last example, NH4, that is also a polyatomic, and the way we know that is because it is on, or in parentheses. So we're going to look for that at the back, and it is our only cation that's a polyatomic. So what I have started to do is the charges for step 2, and then crisscross step 3, rewrite the formula. They each have a 1. No reduction necessary. They each have 1. So real quick before I move to the next slide, what I want you to notice here is that for like this one, there was a 3 plus and a 3 minus. These are the same number. It's going to reduce to where we write no numbers. We have a 2 plus on this one and a 2 minus. They're the same numbers, so it ends up being to where we just write no numbers. So anytime you have the same number opposite charge with your ions, our formula will end up containing no numbers. Alright. In our last 3 examples for writing formulas, we see the names of the compounds given. So now I need to look at the name, and that will help me to identify the elements involved. So magnesium and nitride. The IDE is going to be dropped, and we're going to look for the NITR, and that is nitrogen. That's how I identified the element I'm using. Then I'm going to add the charges, and then crisscross. And then write out the formula, Mg3N2. It will not reduce. And then when I check the charges, I have 3 magnesiums, and that's times 2 plus. And then I have 2 nitrogens times 3 minus. Oops, that's a 6. There we go. So we have 6 plus 6 minus, and they are balanced. Great. Aluminum nitrate. Notice that this ends in ATE. So a quick thing. Names ending in ATE, last names I should say, ending in ATE or ITE, these are on the back of your periodic table. If you'd like to write that on the front of your periodic table, you may do that so that you have that gentle reminder that anytime you see 8 or 8, you're going to look on the back. So we have aluminum and we have nitrate, and we're going to look on the back of our periodic table for nitrate, and we see that it is NO3, and it has a 1 minus charge, so I'll go ahead and put that on there since I'm looking on my periodic table. Aluminum has a 3 plus charge. Now we crisscross and rewrite. Aluminum received a 1, we don't write 1s, NO3, and then nitrate received a 3 from aluminum. I check to see if it reduces. It will not reduce because there is a 1 in the formula. And then I check to make sure they're balanced. I have 1 aluminum, and aluminum has a 3 plus charge. And then I have 3 nitrates, and nitrate has a 1 minus charge. So I'm all balanced. Okay, our last example gives us an opportunity to practice those transition elements. Copper is a transition element. When you see copper on your periodic table, it's in the yellow zone. Yellow means variable. So remember, the Roman numeral told us the charge on copper. So Cu is the symbol for copper. Oxide, we drop off the IDE, we look at the OX, and we see that that is oxygen, so it's an O. Because of this Roman numeral, that will give copper a charge of 2 plus, and then oxide has a 2 minus. We crisscross, we rewrite, we reduce, and we check. And we are balanced. So that ends our discussion of writing ionic compound formulas. And now we're going to look at naming those formulas. All right. In every ionic compound, we're going to have a cation and an anion. The cation is typically the metal, and it will always be written first. The anion will follow. So when we name cations, we're going to write the name of the metal, or the element, I should say, and then add the word ion afterwards. So when we look at sodium, for instance, when we look at the formula for sodium, that means its charged state. It's Na1+ because it lost one valence electron. And we would write out the name as sodium ion, because metals, we just write the name of the metal. Looking at aluminum, what's happening with aluminum is that it loses 3 valence electrons, becomes +3 charge. And we would write out aluminum ion for its name. And then magnesium. Magnesium is going to lose 2, so it becomes 2 positive. And it's a metal, or a cation, so we would just name it magnesium ion. Alright, so that is the simple cations. We do have some polyatomic ions that are cations. So even though I'm talking about the polyatomic ions in the cation section, please realize that there are anions that are polyatomics, and we're going to treat them the same way. So we'll refer to the back of our periodic table when naming polyatomic ions. So find NH4, and when you do, you will see that it was called ammonium. When we look at HCO3, we see that it's called hydrogen carbonate, and then in parentheses it says bicarbonate. Let's just go with a shortened version of its name. Perfectly acceptable, but it's a lot less to write. So we're going to name HCO3 as bicarbonate, and we're getting this information from the back of our periodic table. And then the last one, CrO4, we'll notice when we look for that it's called chromate. So for the polyatomics, no matter what, if they're positive or negative, when we're naming them, we are just going to use the name given on the back of our periodic table. Easy peasy. Alright, before we talk about the transition metals, I need you to go ahead and fix your table because I had an oopsie. Get rid of these here. We just want to know what the element is: iron, tin, and cobalt. And then I would have given you the formula. So I would have given you Fe 2+, and then tin 4+, and cobalt 3+. So that's actually what you should have started with. So I'll give you a second to get that wrote down, and then we'll go ahead and talk about our transition metals. So remember that our transition metals have variable charges. And so we use the Roman numerals to indicate the charge on the metal. And we might have to do a reverse swoosh in order to determine that charge. So the Roman numeral equals the charge. And also remember that lead, tin, and antimony are also going to be treated as if they are transition metals. So we will always use Roman numerals to indicate the charge for the transition metals and lead, tin, and antimony. Alright, so looking at our formula for iron, we see that it has a 2+ charge, which means when I'm naming that, I'm going to write iron and then in parentheses the Roman numeral 2 to indicate the charge. So that's the first name, and then we're going to go ahead and add the word ion. And then for tin, we see that it has a 4+ charge, So we'll use the 4 Roman numeral and add the word ion. And then we have cobalt, and the charge for cobalt is 3, so we'll use the Roman numeral 3 and add the word ion. So here, just real quick, I want to remind you that the Roman numerals are listed 1 through 6 in order on the back of your periodic table under the transition metals section. So if you need help with your Roman numerals, there you have it right on your periodic table. We're going to you might not be given the formula, so you might have to do a reverse swoosh at some time. So maybe you had the formula Fe3N2. The way you would find out the charge on iron is look at nitrogen. Because if you'll remember, when we formed the formula, when we formed the compound, iron gave exchange numbers with nitrogen. So this 2 actually belongs to Fe. So it'd be Fe2 plus. So that's how we could get to the name. And we'll practice that once again on a future slide. Alright, we're talking about the last name now, the anion. This is the nonmetal, or the polyatomic. When we name anions, we're going to write the name of the element, the root of the element, but we're going to change the last piece of that to IDE. So we're going to drop part of the name and replace it with IDE. So oxygen becomes oxide. Oxygen becomes oxide. So we're going to drop all of this and add IDE. Nitrogen, for example, drop all of this and it becomes nitride. So that's what we're talking about. We're going to drop part, we're going to keep the root and add the word IDE, and of course, to finish up the anion, we've got to add the word ion. So this is going to occur in groups 5A, 6A, and 7A because those are the elements forming anions. When we look at bromine, we see that it has a Br1 minus as its formula. It's negative. We know that we need to change it to IDE. So we end up with bromide ion. Arsenic is As3 minus, and it becomes arsenide ion. I'm saying them funny just to help you become familiar with those drop-off points. And then oxygen, oh, I already did oxygen up above, but it's an O2 minus, and it becomes oxide ion. Alright, so that's how we're going to do the anions. But remember, if it's a polyatomic, we do not change its name. We just write down the name listed on the back of our periodic table. Now we get to put it all together and write the name of the ionic compound. When we do that, we've got to make sure that the metal is first, followed by the nonmetal, and we are not going to write the word ion for either of them. In our example, aluminum ion and bromide ion becomes aluminum bromide. So when we look at this first example, we have an H and a Cl. The first is the cation, and we just write the name of the element. No changes. And then we look at chlorine, and chlorine is the anion. It's negative, so it becomes chloride. And there's our first example. And then we have this guy and this guy. Note we have parentheses here, so we're going to look at the back of the periodic table for that. But sodium is our metal, and we don't write, or we don't change the name of the metal. And then when we look at the back of our periodic table, we see that PO4 is phosphate. Alright, I want you to be really careful because notice that if you're looking at the back of the periodic table, you notice that for chlorine, you're going to have chloride and then chlorate and chlorite. ATE, ITE, and IDE. Same will happen for phosphorus. So it becomes, we've got phosphorate, or phosphide, phosphate, and phosphite. So just be careful in how you're spelling them and make sure that it's neat enough for me to read. And then our last example, copper, and then this guy. But when I look at copper on my periodic table, I notice that copper is in the yellow zone. When it's in the yellow zone, that means I must have a Roman numeral. And remember, reverse swooshing tells me that this number is the charge for copper and is my Roman numeral. And then my last name, NO3, is nitrate. Oops. I don't know if I can erase that. Let me just do this. Nitrate, nitrate. Okay, guys, that ends our discussion of writing ionic compound formulas and naming them. Good luck, and see you in class.